Thank you for the introduction, and thank you very much for being here and for inviting me to come and tell you a little bit about the research we've been doing in the past few years, both when I was still in Berkeley, which is when some of this started, and more recently at UIC. So you're going to see a bit of a history of the measurements that we started being able to do and how we've branched out into being able to apply other techniques to look at similar phenomena. The overarching theme is the idea of following an electrochemical reaction that happens in a single particle and that is of relevance to a battery application. So I'm in a chemistry department. I won't claim that I know everything about the techniques that I'm going to be showing, especially not to this audience, but I'm going to be focusing more on how those are being useful to understand better what happens inside a battery. And so I'll start by acknowledging the fact that I'm here standing in front of you giving this talk, but this is the work of a really tremendous amount of people, primarily Young-Sang Yu, who used to be a postdoc in the group. He's the one that pushed some of this work forward when we were still in Berkeley. And we have two students, Mark Wolf and Brian May, who are currently doing some of this imaging work. And the first set of data we ever got, it was done by Ulrike, who's now back in Germany. The other people that you see here are collaborators. These are all synchrotron measurements, and if it wasn't because of people like you that have partnered with us and have been patient with us while we were trying to get the information we needed, none of this would be possible. And so this is just a list of people that were involved from different user facilities, and you'll be seeing data from all of them with the logo so that you can know where they came from. This work is funded as part of an EFRC, so you see also collaborators at other universities, and that's because some of the problems and questions that we try to address in an EFRC are big enough that you need to bring multiple people with different expertise. And so that's I like having the funding acknowledgement out of the way early on so that then I can focus on the actual research. Like I said, this is funded by the Northeast Center for Chemical Energy Storage, which is a DOE EFRC. And DOE is also, as you know, what makes all these user facilities that we take advantage of work. So a little bit of context before I go on to show some data. Like I mentioned, we're trying to generate novel insight into battery reactions. And when you're deciding what to look at, you want to be able to frame it in the context of what a given technology is facing as challenges. And so this is a somewhat outdated plot that is used by battery engineers very often. It plots the specific energy of a given battery against the specific power. And so it tells you, if you think of a battery that powers a car, it tells you how long you can drive the car and how fast you're going to be able to accelerate to the maximum speed that you want to get in. And so, of course, for an ideal battery, you want to be up here, high energy at high power or at all powers. In reality, all batteries behave the way that, like an inverted hockey stick, the way that you see them in this slide. They all, at a given amount of power, will start losing energy. Think of it as the battery not being able to keep up with what you're trying to do with it. And so, like I said, this is somewhat of an outdated slide, but it still makes the point. This little star here is a star that was placed by DOE, identifying what level of storage was necessary for electric vehicles to really penetrate into the market and be competitive against the combustion engine. And so these maps all the battery technologies against that star, and it clearly shows that we have yet to come up with a battery that gets us to that point where we would want to be for all vehicles to be electric. And so that sets the context for what we try to do in our work is how do we build up knowledge that gets batteries with a higher capability for energy storage. The energy of a battery is very easy to define. As a chemist, it's one of the first things I teach when I teach electrochemistry. The free energy of the electrochemical reaction is what defines the energy storage of a battery. And so that's going to be proportional to the amount of electrons that you can exchange, the Faraday constant, and then the difference in potential between the two electrodes that you're using. And so if you want to maximize energy, you want to maximize the amount of storage in terms of charge and the potential difference between the two electrodes that you're using. And so how do you get there? How do you increase that energy density? How do you increase that potential or increase that amount of storage? There's two ways of approaching this, and they're quite discrete. They're approached by different people to some extent. I like saying that the one on the left is the one that engineers follow. Engineers like not having to change anything in their plans. They just want to use the same materials and just do things a little differently. And the one on the right is the one for us geeks chemists that love playing with the periodic table. So the idea with the one on the left is that if you calculate your energy based on the free energy, you'll get a line. Right? So that line would be somewhere around here. But that only takes into account the two electrode materials. A battery is much more than that. You need an electrolyte to get a battery to work. You need to package the battery. It's not suspended. The electrodes are not suspended in air. You don't even see them if you look at a battery. You need safety features. The more energy you pack in a battery, the more you have to keep control of it so that it doesn't go out of range and starts degrading in a catastrophic way. So if you've all seen the pictures of the Boeing fire and various fires that occasionally come up, the hoverboards, all these are battery-related fires. So that's a battery gone wrong because of the way that it was prepared or the not appropriate safety controls. And so all these things are dead weight. They're not giving you energy, but you need them there. So they're actually diluting your active material. They're reducing your energy density. And so that's why when you look at the actual practical densities, they're far away from those theoretical values. You always pay a penalty, and there's no way around this. You'll never get to the theoretical, because you'll always need packaging, or you'll always need an electrolyte. And so what happens at the level of engineering is that engineers have gotten really, really good at putting batteries together. So with minimal changes in chemistry, this is what lithium-ion technology has been able to do. Okay? That's the evolution of the practical energy density. You see this significant upward trend in this decade. And that's just good engineering. It's just being very efficient with the way that the materials are put together. One of the ways that is done is by making the electrodes as thick as you can. If your two electrodes are very, very thick, they have more material per unit of mass in the battery. And so that raises your energy density. The problem is that there are thicknesses above which your electrode performance degrades. So then you've basically created another problem. You can theoretically pack more energy there, but you can't get it out because the electrode is not functioning. It's too thick. We don't understand how electrodes function well enough to know how thick we can make them or how to make them thicker. So that's one possibility. The other one is say, well, if your theoretical bar is here and you pay a percentage penalty by the packaging and the electrolyte, just move your theoretical bar up and that'll drag the practical energy density. And so that's what people like me do. We love the periodic table. We love going from one element to another. And so this is the product of that. This is a map, quote unquote, of electrode materials as identified in a review in 2010. These are the materials that were considered the most relevant. It's not everything that's been tried. But you can already see how busy this plot is. It tells you the capacity. This capacity value in milliampere hour per gram is basically is proportional to the mole of electrons that are being exchanged per unit of gram. So think of them as a unit of charge. And the potential. And so what you will do is pick an electrode material that is down here at low potential and one that is up here to maximize potential. But as you can see, when you're at the high potential region, your materials are really limited in the amount of charge that they can store. So what we really, really need is a material at high potential and high capacity. And that's one of the thrusts that exists today in battery research, is discovery of materials that get to that corner. We're already at the bottom right corner for the negative electrode. People are still pushing this further out of the graph, but where you really have a payoff is by getting to this corner here. And so I like this graph for two reasons. One is because as somebody that does characterization, I can go to you and say, okay, what material do you want to measure? What do you need in the beamline to get a signal? Do you need a particular transition metal? Do you need a particular structure, a particular size? And because a lot of materials have been tried in batteries and a lot of them are relevant, we can always make the case that our case is relevant. Our data is relevant. We need to get this published in a very impactful journal. The other message of this plot is that if we have so many possibilities, it's because clearly we haven't found the one that will solve the problem. And so part of that is that we don't know enough about what limits these materials and what limits the storage of materials to be able to say, okay, this is the atomic features we're looking for, and these are the elements that we need. And so that's what leads us to a unifying theme in both cases. We need new materials or new ways of assembling materials, but if we don't know to the greatest detail how they function, then it becomes difficult to design anything in a way that is really targeted and addresses the problem. You're left with things that are, approaches that are more based on intuition or just trying things and seeing how they work. So traditionally, the way that, when I started my PhD already in batteries in 2000, so back then, the fancy characterization measurement for batteries was to look at the atomic structure. You would just try to create a cell where you could get some information out of the material that told you where the atoms were. And so that's what diffraction does. And so traditionally, diffraction has been the technique to study battery reactions, bulk diffraction. And so I'm going to discuss an example of what you can learn from that that will allow me to set the context for the imaging part of the talk. So this is an atomic arrangement of a spinel oxide. Spinels are very popular in batteries. This is a spinel that has both nickel and manganese. And as a solid-state chemist, this is a system that is a lot of fun, because nominally nickel and manganese are going to be in your octahedral sites of the spinel, but they can arrange themselves in different ways. They can be completely ordered, or they can be completely disordered, and things in between. You can do measurements that tell you that you have something in between. And so the other thing that can happen with this material, the other kind of defect that you can have, is that it tends to have an understoichiometry of nickel. If you count electrons in this composition, you'll come up with the conclusion that this must be nickel 2 and manganese 4. And that's what they are. But manganese has this habit of reducing somewhat with temperature, and these are made at high temperature. What happens with that is that you end up with a little bit of manganese 3 and a little less nickel in the structure to compensate. So they're slightly nickel deficient when you make them. It's very common. It's very difficult to get to stoichiometric materials. So you have these two types of defects. And if you look at the plots on the right, that's just telling you a correlation between these two parameters and the performance of the material. This is a plot of power. What I'm showing here on the y-axis is how much storage capacity do you preserve at a very fast rate. So it's at the top right corner of that plot that I showed you in the beginning. And so that tells you something about how good transport is in this material overall. The x-axis are expressions of these two defects. When manganese is in manganese 3 form, it's electrochemically active. You can oxidize it to manganese 4. And that gives you a signal, a potential that is distinct from the oxidation of nickel. So you know how much manganese you have just from that process. This voltage gap has to do with the way that the voltage profile looks for this material. And I'll show you a couple of voltage profiles next. But just believe me when I tell you that the higher the voltage gap, the more disordered that material is. So if you plot that electrochemical metrics against these two chemical parameters, you'll see that the correlation is much stronger with structural ordering than it is with the amount of manganese 3 defects. And the question is why that is. So we turn to diffraction. This was done at SSRL, and this is very simple. You take a coin cell like the one that you can buy in the supermarket, you drill a hole through it, you put some sort of window, and you let your X-rays through. Very low-tech experiment. And so we get diffraction on the other side. That's the electrochemical curve that I was talking to you about. So whenever you see a battery paper, you'll see curves like that. These are just plots of the free energy with composition. And so this is the amount of electrons that are being removed when you go up, and when you come down is the amount of electrons that are put back in. Okay? the shape of the curve depends on the shape of the free energy curves for that compositional space. When you're going from lithium 1 to lithium 0, what phase is formed when will determine this curve. So it's an interesting curve, has a lot of plateaus going on, and that tells you that there's multiple steps during this phase transformation. When you do diffraction, you see that in the initial step, your diffraction peaks are shifting constantly. This is what's known as a solid solution mechanism, until a given critical concentration where you have a second phase nucleate, and then it becomes a first order transition. You keep removing lithium and you have coexistence of two phases until the point where you don't have the first one, and then a third phase will nucleate. And then you have another first order transition that just carries you until the end of the delithiation. If you bring it back down in potential, then you get the reverse process. This is the voltage gap that I was just talking to you about. This separation between two plateaus gets smaller when your material gets ordered. And so what does this is a disordered material that I'm showing you here. What does an ordered material look like? Well, if you plot the same cell parameter information for the ordered material, first of all, you see this decrease in the voltage gap. It's the same kind of plot, and now your two plateaus are much closer. And now you see that the initial solid solution region has disappeared. And you have a significant difference in lattice parameter between the first phase and the second phase, much bigger than here. And so people that are in the habit of thinking about mechanics will automatically raise their hand and say, oh, yes, you have one particle where there's two-phase coexistence, there's a lattice misfit, there's strain, there must be some sort of mechanical event that is determining the performance of the material. These materials undergoes more strain than this one, and that's why this one is the one with the better performance, with the dots at the top right corner. And so this implies that you have coexistence of two phases in a particle, but this doesn't tell you that you do, at least not the way that we were doing the analysis. And so the question is, can we find out if that's what it is? And so that's what's going to set the rest of my talk. Now I'm going to tell you about all the different measurements that we've tried to do over the years to answer that general question. I'm going to spend quite a bit of time talking more about development and how you make these measurements. And toward the end, I'll drift more toward relevant application materials. So for a little bit, I'm going to be talking about transmission X-ray microscopy. I don't think I need to explain much about this to this audience. But we've used this technique both in the full field mode and scanning mode. We started this work at SSRL, but now we use the TXMs out here in 8BM and 32ID as well. And so what we do is that we can't do anything with morphology. We're chemists. We don't really understand morphology. We understand chemistry. And so it's very important for us to be able to combine that imaging measurement with some sort of chemical probe. And when we started this work, the easiest one was to combine with spectroscopy. If you have an X-ray beam that you scan through the absorption edge of an element, you know the oxidation state of that element, whatever you have a spectrum. And so in these particular measurements, you collect images at different energies, and then you integrate the intensity at each pixel for each energy to build a spectrum for each pixel. And then you then reconstruct that spectrum. You can do a linear combination fit if you know the standards. You can do PCA analysis to extract components. There's basically you choose how sophisticated you want to get. And then you can build your map. Both of these layouts are amenable to sample rotation, so you can do this in tomographic mode as well. And I'll show you some tomography during this talk. Where we really went in the last few years was that we started, when we were doing these measurements, obsessing over the same thing that X-ray microscopy is obsessed with, and it's records in spatial resolution. But as I'm going to argue during this talk, we very progressively realized that sometimes by obsessing over spatial resolution, you miss other important components in the system that you're trying to study. And so for us, we need to be able to follow a reaction as it happens And that has an implication of time resolution. And we need to be able to actually follow the reaction. And so we need to follow chemistry. And that you're going to see that there are moments where you sacrifice and you miss important information if you don't take this into account. And so what we think of it is, we think of it as kind of like the fire triangle, that you need 3 components to get a fire. Well, you need 3 elements for a good chemical imaging to provide the insight that you're looking for, at least for a battery reaction. And so I'm going to discuss development that we've been able to contribute to in all 3 sides of this triangle. This is the spatial resolution graph. This is a graph from 2011, I believe, 2010, where it compares, of course, with TEM. But it allows me to set the stage for the fact that when we started this work, the spatial resolution was typically around 30 nanometers with chemistry. Okay. And so with this is where we did these measurements. This is a particle of lithium iron phosphate, one of the battery materials in that map that I showed you before. You can remove lithium and you get iron 2 going to iron 3. And so what happens is that if you stop halfway, you have a mixture of the 2. And then you can map where they are in your particle. The image on the left is showing you what happens morphologically to the particle, and it's fracturing. It's formed these very striking fracture lines. The image on the right is the TXM image, where we did it with a hard X-ray microscope at the iron K edge. And so we reconstructed the spectra with standards, and we were able to assign where the iron 2 was and where the iron 3 is. And so if you look, you're going to see that there's most of the iron 3 on the outer rims of the particle, but you start seeing features, if you zoom in, that run down that are very reminiscent of those fracture points. The problem is that the spatial resolution wasn't enough to know if crack and red line were exactly on top of each other or adjacent to each other. This is where the spatial resolution was. We tried all sorts of tricks to try to put the images on top of each other. It was very hard to tell. And so this to us gave us reason to see what was out there to be able to increase the spatial resolution. It's also useful if you can look at smaller particles than this, because the vast majority of battery materials are actually more on the sub-micron size, and these are up to 4 microns in size. And so that's where development in spatial resolution were needed. And that's when fortunately for us, this happened when I was still in Berkeley, David Shapiro had just landed, and he was really pushing forward to be able to do tachography measurements with some sort of spectroscopic contrast. And so I won't go into the details of tachography because you're going to laugh at me, because that's not my area. But the idea here is that for us, it was a way of doing a measurement at spatial resolutions below 30 nanometers. Their initial measurements gave them 5 nanometer spatial resolution with an ideal object. I believe that they can do 3 now. The question was, what happens now when you're trying to do chemistry? And so they came to us asking for objects to study, and so we gave them one of the lithium iron phosphate particles or samples that we had. Same idea, it's only partially dilithiated, so it has both the iron 2 species and the iron 3 species. And we were trying to see if we could map it within a particle. You will notice first that these particles are already smaller. They're no longer 4 microns, they're sub-micron in the longest dimension. And we're comparing the standard STIXM with Zanes and the tachography with Zanes. So the same crystal measured both ways and what it looks like. And so the way I like to describe this is that if you take the images on your right and you squint your eyes to make your vision blurry, it looks like the image on the left. So that's what spatial resolution does for you. In this particular case, we were fortunate enough to realize that this crystal had a fracture line. You can see it here in the mass contrast, a little easier to see in here. There's actually 2 of them. And when we looked at the chemical map, what the high spatial resolution of tachography told us was that at both sides of that fracture line, if you look down here, it's a little blurry in the screen, but you can see it better in the screen down here. At both sides of that fracture line, there were domains of dilithiation. At that fracture line, it was still pretty much iron 2. And so the way that we concluded this what we concluded from this was that we have a dilithiation front that is going down that flat facet surface of the particle, building up strain up to the point where the particle just fractures, opens up, and it exposes a domain underneath. And that one was not reacted yet. And that's how it continues to proceed. So this gave us clues into the fact that you're solid state limited by, you're limited by the solid state diffusion in your material in these reactions. We kept pushing the technique. These are images taken at 10 nanometer resolution with the chemistry. And so now we can image true nanoparticles. These are 100 nanometers in the longest dimension. These are the large particles that I showed you in the beginning. That's the one that I was just discussing. These are the smallest ones. These two are fractured. These ones, we looked at hundreds of particles in the TEM, and we could only find one that was fractured. And so we think that that one was already broken when we made it. And so what these all revealed is that even though the distribution of domains is not really that different, you still see that trend that dilithiation is happening at the edges of the particles. The big difference between the three sizes was that the two bigger sizes fracture when they dilithiate, and the smaller sizes do not. And so that's something that had been formulated over time about battery materials, that if you make them small enough, they can bypass fracture. And that's one of the reasons why lithium iron phosphate, if you ever read about it, you hear that you need to make it nanometric for it to operate. And so there are other reasons, but this is one of them. Okay, so like I said, like everything that you can do with an X-ray microscope, if you can rotate your sample stage, you can do it in 3D. These are the same small particles that I was just discussing, but now there's many more of them, and this was done tomographically. We rotated the sample stage and we reconstructed the object while maintaining the chemical contrast. And so this is still at around, I believe this was determined to be 11 nanometer resolution based on some analysis of the images. And now you're able to look at the inside of the objects with this very high spatial resolution. The first thing we did is use these measurements to identify where the particles were and what the dimensions were. And so the plot on the right, what that's showing is the level of reaction for each particle. You can see that they all are at different states. So by the way, these are the same objects. It's just a different scale to depict the chemistry. Okay? So it's the same thing. Plotting the same thing, just different colors. What we noticed was not all particles are in the same states. And if we represent the degree of dilithiation of a given particle with the dimensions of that particle, there was a trend for the facet area to correlate with the degree of dilithiation. The larger the particle, the more dilithiated it was in these conditions, but not with the thickness. And arguably, the thickness variation was not very large. These are quite tailored particles. So that was the first thing that we were able to extract from this data. But then we could obviously then start extracting individual particles and starting doing virtual sectioning and looking at the chemical domains inside. These were a little thin to make a lot of argument about resolution inside the particle in depth. But there were a couple of them that were thick enough that we're confident that what we're seeing is within the particle. The states here, this is the result of integrating the overall chemical state of the sample and just based on the ratio of iron 2 and iron 3, extracting an amount of lithium that it contains. And so both of these particles were in the same sample. Again, this was a partially dilithiated sample. We knew the average state, but each particle does whatever it wants to do. And so you can see when it's at very low levels of dilithiation, there's kind of like spots where the reaction is happening, kind of like what I had shown before. When you have a much greater extent of dilithiation, then there seems to be a trend for particles to have more like condensed domains. There would be 2 domains in one particle. These at first seem to be just an observation and nothing else. And around the same time that we did these measurements, there was a paper coming out of Argonne where they modeled this system using in 3 dimensions, using considerations of phase diagram, thermodynamics, coherency strain, and surface wetting. And so this is the result taken from this paper. And what we found intriguing is that in their case, they were seeing similar effects where at low levels of dilithiation or lithiation, there would be spots in the particle that were active. And in the intermediate states, you would see more like condensed domain. So this makes us think that some of the observations that we're making here have to do with the fact that these particles are in an architecture. They're not supplied by electrons and ions the same way. We have carbon, and carbon doesn't touch this whole particle. It may touch an end of the particle. So think of it as a problem of wiring. They're not wiring perfectly, and if they're not wired perfectly, you may have points in your particle that are reacting more than others. And that's what, based on the theory that was developed and our observations, that's what we concluded. Okay, so I've made a case for spatial resolution. This is something that you would all, those of you working in microscopy, have worried about. The next area that I want to address is the area of chemical resolution, because I will confess that this was something that made us look a little bad, but I'm still going to show you the data. On the left is the original particle or types of particles that I showed, the first chemical image that I showed you, those 4-micron particles in a full-field TXM microscope at the K edge of iron. And so what we truly get in those measurements is an X-ray absorption spectrum of the iron. And so we're able to tell how much iron 2 and iron 3 there is. But in terms of making arguments about crystallographic phases, technically, we're not getting that information. It's a local measurement, a local coordination sphere measurement. And so typically, iron 2, iron 3 are associated with lithium iron phosphate and iron phosphate. And we didn't see evidence of otherwise. There were two components. We did PCA. There were two components in this structure. So we interpret this as a mixture of lithium iron phosphate and iron phosphate. For a variety of reasons, we wanted to be able to get similar insight, but now using diffraction instead of spectroscopy. Diffraction has the added component that you can look at strain, and when you're worrying about mechanical events, measuring strain is very, very useful. And so this was done at the nanoprobe here at Argonne, beamline 26, where we have a small beam that is being scanned on the sample, and then there's a detector that detects the diffracted intensity. And then we rock the particle around a diffraction peak to see where that diffraction peak appeared in 2 theta. Okay. And so depending on the 2 theta, because we know the system very well, we know exactly what lithium composition we have. There's plenty of data in the literature to compare. Given position of the 2 theta, given D spacing, that's the compound you have. And so if this is what this image is representing, that's the diffraction intensity for the whole particle. So these are all the individual mapping positions added together into a pattern that is the overall pattern of the particle. And so if you have 2 phases, you should have 2 peaks in 2 theta. And we see 3. We not only see 3, we actually see a continuity of intensity in 2 theta between the one on the left and the next one. And so what this told us is that these particles, which were exactly the same as the ones that I'm showing you on the left, we interpreted them as mixtures of lithium iron phosphate and iron phosphate, but in reality, they had a solid solution. They had an intermediate composition that has also iron 2 and iron 3 by virtue of being intermediate. And what we think is happening is that iron 2 and iron 3 in those structures are quite clustered, so that they almost look like isolated iron 2 and isolated iron 3. You need a lot of energy resolution to be able to tell if you have iron 2 and iron 3 in the same structure or in different structures. In the TXM experiment, you're limited by how much beam time you get. And so you would get, 15, 20 energy points. It's not enough to get the energy resolution that you would need to discern the 2 phases. Diffraction doesn't have that problem. You're really very sensitive because you have a large 2 theta separation between the states. Not only there's an intermediate, but there's miscibility between the full lithiated state and the partially lithiated state. And this creates a whole set of questions about what we knew about this system, perhaps the most studied system in the battery business. But I won't get to those details. I'll just proceed to show you what we did with the microscope, we not only used it to say, oh, there's 3 phases, or there's 2 phases plus a miscibility domain. We then located those phases in the particle. And that's what you can do when you then, instead of looking at the overall pattern, you look at each individual pattern for each position. You can assign a 2 theta in a composition. And so what I'm showing here is what domains lighten up when you're integrating your signal at a different angle. And so it tells you where lithium iron phosphate is, when iron phosphate is, and where the intermediate compositions are. And so if you look and remember what I was just showing you, there is a trend for the iron phosphate to be at the edges, the same thing that we saw in the TXM measurement. But now what we see is that in the inside, where we thought we had domains, where we had 2 phases mixing, in some cases, it's actually 1 phase with both oxidation states in the same unit cell. And so these to us, we were not looking for this. This just happened to be what the measurement told us. And to us, it was very revealing of trying to avoid taking shortcuts when you're doing your TXM measurement, just to get faster measurements, collect very few energy points. You run this risk. You may lose chemical resolution in moments where it actually matters. The last side of the triangle is time resolution. This is self-explanatory. We're doing a reaction. Reactions evolve with time. How do they evolve? Back to the plot that I showed you before, if you think of in terms of how you're going to build a reactor that you can get signal in and out of to be able to measure this, well, this is a plot of penetration depending on the X-ray radiation that you're using. And so in the hard X-ray regime, you're penetrating through scales that allow you to start building cells with electrolyte and separator and lithium and still be able to get your beam through to get a transmission signal. So that's what we set out to do. We're not the only ones that did this. There's a number of papers on similar measurements. Our idea was to try to maximize signal. And so what we did is that we put isolated particles with a very well-defined shape, because then by just looking at them, we knew exactly their crystallographic orientation. This is basic mineralogy. And so very defined shape, right size, so that we could get multiple data points within the same particle. And then we mounted them on a copper TEM grid, and copper is conductor, so that's your current collector, and did the reaction on the copper TEM as opposed to building an architecture with carbon and PVDF, which are light, but they still contribute to some absorption. This is a very simple cell. It was the same that I showed you with the diffraction experiment. Drill holes to the coin cell, silicon nitride window so that you don't have lithium exposed to air, primarily. So that's just safety. And so this is a different material. This is a manganese oxide, again a spinel, but it's not a spinel with nickel, it's just manganese. We're still removing lithium all the way to lithium 0. So we have manganese 3 going to manganese 4. This is an experiment done at the manganese K edge. So we collect 2-dimensional images, and then we scan the potential. That's the electrochemistry plot that you get. And so we know at what potential, what redox state we have for manganese, and that tells us what the reaction is doing. The signals are very washed out because the number of particles is so small that there's almost not enough particles to give you a measurable electrochemical signal over the background currents that you have in all electrochemical measurement. So you can see examples on the right of particles that are at different potentials and how they're evolving from being lithiated to being completely lithiated. And again, that image on the right is nicer down here. But there's a mixture of red and blue with the same shape as you see here. Because we're doing imaging, we're also getting morphological information, and in this case, it was interesting to, again, locate areas where the particle was fracturing and opening up enough that we could tell that it was fractured. So now you can start making correlations between mechanics and chemistry in these kinds of systems. The other really intriguing thing that we found here was that by doing the reaction under working conditions, we started seeing states that you wouldn't really predict are possible. And so just slowing down for a minute and telling you what this material does. You can actually start from a lithium 2 state, which is all manganese 3, and that's how we actually started the experiment. And you can, this equation is, this should be a 1. you can remove one lithium and go from lithium-2 to lithium-1. This happens at 2.9 volts. So if you then want to know what the free energy is, you multiply by Faraday constant and the number of electrons. If you keep going, you can remove another lithium, and that happened in 2 steps, just like I showed you for the nickel phase. You get a 0.5, and then you get a lithium 0. And those happen at 4 volts, very close to each other, only separated by 10 millivolts. And so the image that I'm showing in this slide is just one snapshot at one potential in the cell. So that's the image on the left. The images on the right are concentration plots. So this is basically taking one of the phases that we found in the sample by doing linear combination fit and plotting the concentration in the particle. And so this plot in the middle is this Li.5 phase, and the plot on the right is the Li2, which is all manganese 3. And so you can see that in the same particle, both phases are present. They're far from each other, but this is a 4-micron object. And look at the difference in potential between the two. Lithium 0.5 exists at 4.05 volts. Lithium 2 exists at 2.9. You have a potential drop between your particle that is over a volt. So this was one of those things where you look at the data and say, yeah, this just can't be. This must be wrong. I can show you the spectra if you want to see it. There's no other way of explaining it. And so what we concluded that was going on in here is that we have this particle that is quite high. It's an octahedron, and it's about 4 microns in the longest dimension. So gravity dictates that it's going to most likely fall on one of the faces on the grid. And so it's not completely in contact with the grid, and the grid is the only place where the electrons can conduct. There's nothing else. There's no carbon in this. And so what we think is going on in this particle is that this end is touching the TEM grid. And that's where the reaction can start easily, and electrons can be removed. But from this tip, they have to conduct through the material, and this is a semiconductor. And so the reaction gets delayed significantly because there's a kinetic hindrance for the electrons to move from one end to the end that is in contact with the circuit. And so this is an example of why you want to do measurement operando. We could argue that these are very extreme situations with very poor contact, but if you want to get batteries with very high energy density, you may need to reduce the carbon amount so much that you may have situations like this where there's a particle that is very poorly connected to the electrical circuit. Okay, so this is great. Very varied set of experiments. You can beat different barriers in different areas of resolution. But so far, all I've done is say, okay, we want to do this measurement. What material do we study that will allow us to make this measurement? So that pretty much here is where I moved to UIC and other things started happening. And so now the question becomes, what do you do with these techniques to answer questions that really matter to the battery engineer that is trying to design a battery for a 300-mile car? And so for that, we turn to focusing on a different set of systems. These are lithium metal oxide systems with that stoichiometry that I'm showing on the slide. These are layer systems. These are by far the most popular cathode materials in a lithium-ion battery. M can be almost anything. Right now, the most popular combinations have nickel, cobalt, manganese, aluminum maybe. And so these are the phases that constitute the most focus for application. And so theoretically, you could do the reaction in the top. You could remove one lithium and go to MO2. That would give you 280 milliampere hour per gram. That's right at that top right corner of that map that I showed you. But that's what reality is. You don't get to 280. The more lithium you remove beyond this point that I'm showing here, the more likely you are to have a battery fire because it's becoming really, really unstable and it starts letting go of oxygen. Not only that, when you go and delithiate and you then are trying to relithiate, the more lithium you remove, the less you get back in. There's something happening to the material that degrades it and doesn't allow you to get to recharge that material. So your battery will progressively lose range. And so in the EFRC, we're really focused, in Nexus, we're really focused on this problem, the problem of closing the gap between theoretical capacity and what we're actually able to get. How close can we get to that 280 milliampere hour per gram? And so part of what we're doing is applying the operando measurements that I just discussed to these particular systems. Now, instead of looking at a single crystal, I'm looking at an agglomerate of primary particles. This is how commercial materials look like, by the way. They're meatballs, literally meatballs. They really look like meatballs. They're round, they have small particles, and they're really densely packed. And so in this case, we're not able to resolve the primary particles, but we're able to see how these particles go from lithiated to dilithiated by following the nickel oxidation state. And so on the left is a snapshot at one point of the reaction. This was done here at 8 p.m., where you can see a particle that has a heterogeneity, where it's kind of, some parts of the particle are more oxidized than others. The other interesting thing that you can do with this measurement is that because we can have multiple particles in that field of view, we can then integrate the overall state of that individual particle. How oxidized, on average, is nickel in that particle? Not locally on those spots, that's what I'm showing on the left, but on average in that particle. And then compare how nickel gets oxidized with respect to the signal of the cell and with respect to the other particles. So this plot on the right, what it's showing is the cell being charged. And when you charge it, your potential goes up. You're removing lithium. But you're removing lithium from anywhere in the cell. And we're only imaging, what, 6 particles? There's many more in that cell. So those are not the only ones that could be contributing charge. The interesting thing is that when you remove lithium, these particular particles didn't seem to do much until a critical point, and then they just jumped. They reacted so fast that we did not have time to catch the inhomogeneity. This snapshot here is this point here, this thing here. It's this particle here. So each dot is a different particle. That's the only one, if you can see, or this one too, but that's the one that gave us the clearest point where we were in the middle of that quick jump. And then once they reach a given oxidation state, they keep oxidizing much more slowly. And so not only that, if you look at different particles, they're doing it in different time sequences. They're not all going at the same time. This is kind of random. There are other measurements where they go much more conserved. And this probably reflects the balance of how much electrolyte you have in that area of your electrode, how much carbon you had in there, how well the electrode was made. It's probably a lot to do with the way that the architecture was put together. But this is a measurement that we've repeated multiple times, and we always see the same behavior on that first charge. We think what happens here is that the surface of these particles, they tend to form layers in contact with air that are insulating. And we think that there's a blocking effect, that you need enough energy for the particle to have a driving force to dilithiate. And once it goes over that insulating layer, it has so much driving force that it goes very quickly. That's the way that we're interpreting this. That insulating layer could be lithium carbonate. If that's the case, by the time you've charged it, it's burned. Lithium carbonate is not stable at these potentials. And so that could explain why when you go on discharge, when you reduce again, the particles transform progressively, which is what we would expect based on the mechanism at the bulk average for these materials. And so this is an example where all particles went at the same time. It's a different measurement. They go at the same time, they kind of keep going a little bit while you're charged, and when you start discharging, then they go progressively. And we think that this is because that insulating layer is gone, and now lithium can move freely in and out. And then you're much closer to a thermodynamic condition. You're not in conditions that are kinetically imposed by port transport, which is critical in a battery. So is this true? Is this two-phase? Is this one-phase? What is it? And so this is going to be quick because there are very recent measurements, and we haven't analyzed the data, but just to show you things that we've been able to do with it. Going back to the problem of identifying whether that jump is due to one-phase transformation or two-phase transformation, that inhomogeneity that I showed you, we turn to diffraction again. This was done at 34 IDE. This is the Ampix cell that a lot of you probably know. Was modified so that we could map with a sub-micron beam different spots in a particle and get a diffraction pattern of every spot. This was done with a monochromatic beam and an image plate detector on the back. So we're getting powder rings and integrating those rings. This is the data. Again, this is just data that literally was just given to me last week. where we can resolve the particles being oxidized, and then we can also do the same thing that I did before, where we integrate the overall diffraction pattern for the whole particle, and we can see the diffraction peaks evolving as the lithium is being removed. These are evolutions that look very similar to what you get in a bulk diffraction experiment, but we're still comparing the details to make sure that everything looks pretty much the same. Okay, so I've reached almost the end of the talk, and I've talked a lot about doing measurements in transmission, and that means that I'm talking about doing measurements where we average over the depth of a particle. And if you think of spatial resolution, sure, tomography is a way of getting resolution in 3 dimensions, but even tomography is not giving you surface information. It's still a 10 nanometer piece of information. So when your particles are very thin, or if you want to know what happens at the surface, then you can't do it with tomography either. And so to me, one of the areas where spatial resolution could be improved is by having true surface measurements that have that chemical resolution. And this is where we reached out to Volker, who's in the audience right there. And if you have any questions of how that works, you ask him. But the idea here is that you have an STM measurement that is coupled with the photoelectron generation of a sample when you irradiate it with a beam that is at a given absorption edge. This is, you can do it with any absorption edge. We did it with nickel, and we stayed with those layer oxides that I told you about. And so the idea here is that you're getting much more sensitive information, but you're still able to map a particle, or at least that's our hope. This is data from last week, was it last week that we measured this? So this is really, really recent. But the idea here is to show that we're able to get nickel data. This is the far field measurement. That's nickel 2, which this is a particle that was partially dilithiated. It's not necessarily surprising that it has nickel 2. These are the particles. We did objects that were small and quite flat, so they're 40 nanometers in thickness, so that they were well behaved in terms of dispersion. And the data on the right is basically showing that we can tell where the particle is by imaging at a spot where you don't see morphologically a particle and you don't get any nickel signal. And if you're in the sample, you can get a nickel spectrum. Now we can take these nickel spectra and interpret them based on whether it could be nickel 2, nickel 3, or nickel 4. And that will tell us what the surface of that electrode, or the near surface of that electrode, in what state it is. And then we can compare with measurements of phycography, which we've done, which give us an average over the depth of that same object. It's the same exact object at the same exact edge. And so this is something that, to me, is a very exciting prospect for the future, because it addresses an area that we were basically not able to get information on so far. So that's my summary slide. The idea of this talk is to convince you that if you want to improve batteries, you're going to have to really look deep inside and worry about how electrode reactions happen from one end to the other of the battery state. The battery is a mysterious box, but inside it's a very simple chemical reaction, quote unquote simple. And so in the end, these are reactions that, as you can see, develop in homogeneities at very different scales. You can have inhomogeneities between particles. You can have inhomogeneities within a particle. You can have inhomogeneities between the outside of the particle and the inside of the particle. Imagine now a structure like your battery that is in your cell phone that is centimeters and has millions of particles and is on top of that 90 microns thick. And think about what kind of variety of inhomogeneity you could have there. These are inherently multi-scale problems that need multi-scale tools, and this is just addressing the single particle component. We do this with X-ray microscopy. It's beautiful what you can do with X-ray microscopy today. You can combine with spectroscopy, combine with diffraction. You can do more like, or we hope we're going to be able to do more like surface-sensitive measurements. And because you can do this in the hard X-ray regime very often, you can design an operando cell that allows you to follow the reaction as it happens with a chemical image. We can go down to 10 nanometers. There's a new beamline coming up at ALS that probably can bring that down a little more. And the idea here is to couple what the chemistry is doing, which is the part that we're interested in, with transport and even mechanics, because the imaging component tells you at least when the particle fracture. If you're doing diffraction, you'll even be able to map strain. And so we're continuing in this direction. I'm showing here a couple of directions that we keep going. One is the scanning X-ray STM, where we're trying to resolve interfacial phenomena. And the other one is that we have a student permanently located at 32ID developing a new operando cell that has the ability to do experiments much more reliably in a much more sophisticated way so that the electrochemistry is reproducible and it's always the same, which has been an issue with those drill coin cells with the windows on top. So that's where we are. I'll stop here. Thank you for your attention, and I'm happy to take any questions.
Anybody have any questions? Ching Cheng.
Yes, it's very nice talk. First of all, would you mind going back to the slide where you show like the different brackets, like during the chart?
This one?
Actually, it's at the beginning of the
Oh, okay. That was an ex situ measurement. That was just one state. Just to clarify while I go there.
Repeat the question.
Oh, sorry. So like basically, if you go back to the like a slide where you're showing the
This one?
Oh, I actually can't see it.
Oh, sorry. Where's my pointer? This one?
No, like
No.
I think it was the one where show like a different like a line plots of the XRD like data.
Okay, let me
And,
see. And the other diffraction, I think, is this one?
The one before that, I think.
This one.
Yeah.
Okay.
So the question I have is like, have you ever encountered any electro materials which like doesn't, in which like the Bragg peaks, the position of the Bragg peaks do not change like during the power cycles?
Well, yes and no. So you're moving atoms in and out of a structure, so the structure is going to respond to it. There is one material that is able to. It's a spinel structure, and the spinel structure is related to rock salt just by having occupancy of the tetrahedral sites. So you can push that atom in the tetrahedral site to an octahedral site and get a rock salt. And so if you put lithium in a titanate that is being used commercially, because it can push the lithium out, it doesn't need to rearrange the lattice as much, and so it's a very small change. It's less than 1% of the unit cell lattice, but it's still not zero. That's the closest I've seen. You would need to have a very open structure for that to work out. The more compact it is in densities, you're going to need to, the balls are pushing each other out. So yeah, so it's not, you can get very low, but you can't really get to zero, I don't think.
What was the chemical formula of the material?
It's lithium 4, titanium 5, oxygen 12. Yeah.
Other questions? Yes, Paul.
So, Jordi, there was one part you were talking about, there was this octahedron-shaped particle with the different, I think it was the iron oxidation states that coexisted.
Manganese. Manganese?
Was it manganese? It was the one where you mentioned there was a point contact and there was a line. Yeah, that one, exactly. So it was manganese, okay. So I didn't get, how is that being stabilized? So you have a voltage gradient which is very high within the particle, so I would expect that would try to relax at some sense. So this is probably long after it's been charged, you've been doing a measurement.
In the next snapshot, it doesn't look like that anymore.
Okay. So this is just during charge?
Yeah, we only did charge in this experiment.
Okay.
It's kind of a strange event. I show it because it just shows how crazy batteries can get inside.
Okay, so it's not being held like that for a long time, okay.
No, that's just a snapshot, and if you keep going, that particle is actually, no, it's not this one, but I can show you the data. That particle kept going, and it just went to the same manganese 4 state. Yeah, this is just this one snapshot. Yeah.
Thanks.
Following along with that question, what happens to the strain or the defects in that particular particle, even over a short period of time? That's quite a bit of field. Does it strain? Does it start cracking more?
Well,
Do you see any evidence of that?
This particle already had a crack here. And the question is, what's first, the chicken or the egg? Did this domain end up here because of the crack, or did the crack end up there because of the domain? And the previous snapshot doesn't tell you that, right? So we don't have quite the time resolution to really see this domain kind of appearing and growing. So I assume that only thinking of the fact that you have an Li2 structure, which is a tetragonal spinel. I haven't said that, but it's a tetragonal spinel. And then you have an Li.5, which is a cubic spinel that is actually smaller than the original material. The amount of strain that you're accumulating in that particle is very large too. Yeah. It doesn't explode though. There's fracture points, but some of them develop by going from lithium-2 to lithium-1. That's already quite straining, because it's an anisotropic phase change.
Any last question? All right, if not, let's thank Jordi again.
Thank you.